let's put some of that information we just learned about a gradient to use on an actual function. So I have a function here of 3 variables, which we haven't dealt with before. The square root of x squared plus y squared plus z squared. And we want to find the maximum value of the directional derivative at this point, 1e pi. And just, picking random numbers out there. So to do that, we need to find the gradient, because what we learned is that the direction of maximal change is in the direction of the gradient. So if we find the value of the gradient and find its magnitude at this point, we will find the maximum value of the gradient. The maximum value of the directional derivative. So let's find the gradient. First, let's rewrite f as that. That might make our lives a little easier. So let's find the partial with respect to x. Partial with respect to y. And the partial with respect to z. And then we're going to rewrite these. So the 2 and the 1/2 cancels on each one of these. And we have this negative 1/2 as an exponent for all these. So this is going to be x over the square root of x squared plus y squared plus z squared. Y over x squared plus y squared plus z squared. And z over x squared plus y squared plus z squared. So those are our 3 components. Let's change markers for a moment and write our gradient. So our gradient takes each of these components and assigns them to the I, j, and k vectors respectively. So the normal way to do this is to go ahead and plug in the point to the gradient. But what if we instead got the magnitude of the gradient? Actually, let's go ahead and do it at the point. Now, I want to point out something once we're done here. So if we get it at 1 pi e, or e pi, one over 1 plus e squared plus pi squared I plus e over 1 squared plus e squared plus pi squared j plus pi 1 squared plus e squared plus pi squared k. So that's our gradient at this point, and then we need to find the magnitude of the gradient to find the maximum value of the directional derivative. So if we were to go along this particular path, if we went along this vector, the directional derivative would have a specific value that we're going to find. So the magnitude of the gradient. Whoops. Sorry, getting ahead of myself here. All right. All right. After all that, the value is 1. Well, let's think about this. So if we go, well, I said let's try to do it in general, because sometimes it actually makes sense to look at the general magnitude of the gradient. Why do we want to do that? Because we might want to know across the entire spectrum what the maximum value of a gradient is going to be, or maximum value of a directional derivative is going to be, so that we might have some idea of a speed of a function over the whole space, you know, whether or not it gets very turbulent, or whether or not it can kind of fly away from you. So to do that, let's compute the magnitude here. So if I did that, I'd end up with x squared over x squared plus y squared plus z squared plus y squared, x squared plus y squared plus z squared plus z squared plus y squared plus z squared, which if you do everything also gets you 1. So what you find is that for this particular function, that directional derivative is maximized at 1 everywhere. So as long as you're following a very particular path, you will always have a constant speed of where you're going. So which makes sense, because if this right here, if this is a fixed value, for instance, then this is actually the equation of a sphere. And so as long as you're moving about, you're going to have this directional derivative. If you move in a particular direction, you're just going to be kind of like traversing a sphere, just any way you go. If you keep going along the sphere, there's not really a faster way to go about a sphere. You're always just kind of going around it. And so that's the idea here. Technically, this is kind of like a hypersphere situation, but this is the same sort of idea. But ultimately, this is how we compute it. This is a bit excessive, but ultimately you're computing a gradient, plugging in a value, taking a magnitude, and that's how you find the maximum direction, or the maximum value of a directional derivative.